We've reached the last topic of this lesson, live scripts. So what are they? A live script is a relatively new way of embedding MATLAB code in documents, or conversely, they can be used to add text and images to your MATLAB programs. Even more importantly, the output of the program will appear right inside the script, making your program seem to come alive, hence the name, live script. And as the name suggests, this tool works only with scripts, not with functions. You may be surprised at that, since we said very early on that our focus will be functions instead of scripts. Well, we're going to make an exception here, because live scripts are very useful in creating small but impactful projects in MATLAB. Let's start with a recap of the differences between scripts and functions. First, scripts do not have their own workspaces. They work at the command line level, which means that any variable that you create or modify in a script will directly impact your base workspace. Second, scripts cannot have either input arguments or output arguments. Because of these two features, scripts are typically used to create only small programs. To introduce live scripts, let's create an example. We'll show some of the most important features of live scripts. However, there's no time to cover everything here. If you find live scripts useful for your work, you'll be able to explore them on your own after this lecture. The example we chose is a hot topic, literally. We'll create a script to illustrate how atmospheric concentrations of carbon dioxide, also known as CO2, have changed over the past decades. We'll also use a simple prediction model to see where we're headed. To do all this, we need data, and fortunately, we can get it easily. In fact, we've already downloaded the data into an Excel workbook. It came from the Mauna Loa Observatory, which is located on the Big Island of the state of Hawaii, which we're looking at here from above courtesy of NASA. The observatory is on the Mauna Loa volcano, which is right here. Mauna Loa has been active for close to 1 million years, with the most recent eruption lasting about 3 weeks in 1984. And in fact, it's the biggest active volcano on Earth. The other volcano here is Mauna Kea, but it hasn't erupted for 6,000 years. The white stuff on the peaks is, well, snow. But it's not volcanoes that we're interested in. We're interested in data on carbon dioxide concentrations in the atmosphere. These data have been collected on the slope of Mauna Loa continually for half a century by the Earth System Research Laboratory of the National Oceanic and Atmospheric Administration, NOAA. And they're freely available from their website. Why is CO2 data collected here? Well, it's because up here, CO2 from plants and local car exhaust and other CO2 sources from big cities are not a big problem, and prevailing winds constantly blow clean air in from the ocean. Yes, occasionally the active volcano spews out CO2, but it's so rare and so obvious when it does it that the resulting corruption can easily be removed from the data. And we've got the data right here in this Excel workbook, which is named CO2 Mauna Loa. When we open it, we see 4 columns. The first is the year, the second is the month, the third is a fractional number that includes both year and month, and the fourth column is the CO2 data. The reason for the fractional version of year and month is that it's better for plotting. As you can see, the first month is March 1958, and if you check the decimal parts, you'll find that it's the middle of March. In fact, every fractional date is at the middle of a month. Each CO2 reading in this fourth column is the mean value measured over the month, and the measured value is the number of CO2 molecules per million air molecules. So the mean parts per million of CO2 averaged over March 1958 was 315.71. A new row is added every month, and if we scroll down to the bottom of the spreadsheet, we see that the last of the measurements were made in January of 2020. You can read all about the data if you follow this link. If you do, you'll see that there's even more data available, but this is all we need to introduce our first live script. Our script is going to plot this data for us so we can understand it a bit better. So the first thing we need to do is create a live script. And to do that, we can just click New Live Script here on the Home tab of the ribbon. Or if your version of MATLAB doesn't have that, you can click on the down arrow here below New and select Live Script. If you're using an installed version before 2016, you won't have that option, but you can always use MATLAB Online, which of course has everything. Notice the name of the file has a new file extension. It's MLX instead of just M. And it obviously stands for MATLAB Live Script. But no, wait, that would be MLS. Either that extension was already being used, or maybe MLX is just more exciting. But in any case, MLX in MATLAB means Live Script. Let's give it a descriptive name. Say CO2 atmospheric concentrations. Okay, sounds pretty good. And now we got a very nice name for a very empty script. Let's put something in there. The gray area is where MATLAB expects us to start adding our code, so let's do it. The first line reads the Excel workbook. If you're not familiar with the function xlsread, or don't remember how it works, you can see our explanation of it in Lesson 8 of our introductory course. But in the simplest case, which is what we've got here, you just give it the file name of the workbook you want to read as a single input argument, and you get as output an array of doubles, with each number in the array corresponding to one cell in the workbook, laid out just as they are in the spreadsheet. If there's a formula in the cell, then the calculated number is written into the corresponding element of the array instead of the formula itself. And what does MATLAB write into the element if the corresponding cell contains text? Well, since text is not a number, MATLAB writes NaN there for not a number. And speaking of text, you might have noticed that we put double quotes around the name of the workbook as our input argument instead of single quotes. Well, either one works, but we've chosen in this case to use the string type instead of a character string, and the double quotes gives you the string type. The string type was introduced in 2017. If you're not familiar with it, you can hear me explain how it works in Lesson 7 of our introductory course. This relatively new string type has lots of nice features, and we discuss them in that introductory course. But in most cases, when a built-in MATLAB function expects a string, it's versatile enough to accept either the new string with the double quotes or the old single quote variety. And we take pains to use both in this video to emphasize that versatility. So the first line reads the numbers in the Excel file into the array named CO2. The rest of the commands are pretty routine. We copied the third column of CO2 into the variable year and the fourth column into the variable CO2 with CO in uppercase. Then we plot CO2 versus year, turn on the grid, add a title, and label the axes. Well, let's run it. Do you see how the plot appeared right next to the MATLAB script? Side by side is the default. But I like it in line more, so let's click this little icon on the right. There, perfect. Notice how the data is periodic. That's due to the seasonal variation across the year, but overall the trend is clearly upward. Notice that if you hover the mouse over the figure, a set of gray icons appear in the top right corner. By clicking the arrow on the far right, you can open the figure in its own window. You can also manipulate the figure in place. For example, click the magnifier icon and then you can zoom in the figure. You've seen us do that before. Once you do that, notice how a couple of lines of code appear on the right. You can click the Update Code button or copy and paste that code in your script, And then the zooming you've done manually will be done programmatically the next time you run the code. I don't want to do that in this case because I want the whole plot to show, but it can be a very useful feature. Well, let's add some description of what this script is doing. Position the cursor in the first line and click the big text button. Type in Mauna Loa carbon dioxide concentrations and click Normal and select Title. Let's type in some more text. You can also insert hyperlinks. Just select the text you want to make a link, click Right, and select the last option, Hyperlink. It'll then prompt you for the URL. I've downloaded a photo of the observatory of Mauna Loa from NOAA. Let's insert that by clicking the big Insert tab on the very top and selecting Image. We pick the file we want, and now we can resize it as well. Let's introduce the code segment we have so far by typing "Let's read the data in and plot it" with a colon, and select Heading 2. Okay, that looks pretty nice. By the way, as we develop this live script, some of you, especially those of you who took our introductory course, may wonder what the relationship is between live scripts and scripts with sections on which the publish option has been used. We introduced that in lesson 6 of our introductory course. Well, we'll explain it. In fact, we'll show you how to convert any non-live script into a live script. But first, let's put some more code in this one. And we're going to add the next lines of code in a new section. To do that, we click Section Break. This breaking of the script into sections allows us to run one part of our code at a time. That's a very handy feature of live scripts, but it's not a new feature in MATLAB. Normal scripts and even functions can be divided into sections too. You can do it either by clicking an Insert button or by adding a comment line that starts with 2% signs. The difference is that live scripts give you a lot more formatting freedom, and as we've seen, allows you to insert pictures and hyperlinks and other things into its sections. So let's put in our heading for this section by again clicking the text button, and let's type "smooth the data and plot it with the original data," because that's exactly what we're going to do. We're going to smooth it to get rid of those wiggly seasonal fluctuations. And we'll do it with a function introduced in 2017 called smooth data. Okay, to get out of text mode and back into coding mode, we click the Code button up here. And now I'll type in the code using my magic miracle lightning fast fingers. So what's going on here? Well, all the work is done on the second line, but first we specify a length of 12 for our smoothing window, meaning that 12 points from the original data will be combined to produce each new point in the smooth data. That window length is the third input argument here in our call of smooth data, which does the heavy lifting for this section. The first argument is the original data, and the second argument is the name of the smoothing method. In this case, we choose MOVMEAN, which means moving mean. Roughly what it does is move the center of the window from the beginning to the end, and at each position, average the points that fall inside the window to get the smooth point in the center. There are several other methods listed in the help documentation for this function as well. You can check that out. Once we get the output from smooth data, we plot the original data in green and the smooth data in black. And once again turn on the grid and give it a title and axis labels. This time though, since there are two lines plotted on the same graph, we add a legend to tell us which line is which. Okay, let's click Run and see what we get. Well, you can see that the smoothing worked. The wiggles are gone, but that upward trend is still there. Now comes the most interesting part of our little exercise. Let's try to predict where we can expect CO2 concentrations to be by the middle of this century. As we can clearly see from the plot, the growth is not a straight line. It looks very much like an exponential curve. So let's try an exponential fit. To do that, we'll use a few functions from MATLAB's curve fitting toolbox, which was introduced in release R2016B. Let's start a new section, give it the heading Model the Growth of CO2 as Exponential and compare it to smooth data. And enter the code. So here's the code. The first 3 lines use functions from the curve fitting toolbox. Fit type is first, and its first input argument is a string stating the formula for the type of curve that we want to fit to the data. That formula has the form a plus b times e raised to the power of n multiplied by the time elapsed since 1958 in years, which is a general exponential function for growth since the first concentration of CO2 was measured at Mauna Loa. The second 2 arguments tell the function that year is the independent variable, leaving a, b, and n as constants that must be determined by MATLAB. Its output is the model to be fit to the data. Fit options is second. Its first 2 arguments tell the function that the method for determining the best values of a, b, and n is nonlinear least squares. The last 2 arguments give the initial values for a and b and n that MATLAB will use in an internal iterative method for finding the values for these 3 constants that will minimize the sum of squared differences between the fit and the input data. Those 3 values are 0, 0, and 0. Its output is a variable that captures those options. Fit is third. Its first 2 arguments are the independent and dependent variables to which the model is to be fit. The model and the options, which come from the first 2 functions, are third and fourth. Its output is a structure whose fields describe the model that has been fit to the CO2 data. The next line uses the fields a, b, and n of the struct CO2_fit to calculate values of the model for every element of the variable year. We assign those values to the vector CO2_model. Now that we have values for the model, we can plot them. To get a visual idea of how well the model fits the smoothed data, we plot both of them on the same graph, with the smooth data in black and the exponential model as a red dashed line. As before, we turn on the grid, then decorate the plot with title, labels for the axes, and a legend. Okay, let's see how well this model fits. Since we've already run the previous section to get the smooth data, all I need to do is run this one section. And I can do that by clicking the icon labeled Run Section. There. Well, that's an amazing fit. You're looking at a real-world prime example of exponential growth. That's a really good fit, and you can put a number on it. In fact, several of them, if you ask for a second output from fit. If you do, you'll get another struct, and its fields contain several statistics. One of them is the root mean squared error, and it equals 2.2, meaning roughly that the average error is 2 parts per million, or about 0.6% of the mean parts per million. Did I mention that this is a good fit? By the way, now that we have 3 plots in our live script, it's a good time to point out that each one has been plotted separately, and yet we have not requested new figures for each of them. If you were to give these 3 plot commands in a normal non-live script or a function or the command window, and do it as we have done here without turning hold on, The second plot would replace the first plot, and then the third one would replace the second one. And in the end, all we would have is one figure with the third plot. But as you can see, that's not how things work with live scripts. Each section gets to plot a brand new plot. Now that we've got such a good close-fitting model, we can use it to extrapolate out to that mid-current century mark. To do that, we simply plot the model from January 2020 to January 2050 in a new section. And here's what that section looks like. The first line gets us the dates in the future with a step equal to 1 month. The second line is similar to the same command we used in the previous section, but this time year is replaced by future. On the third line, we plot the actual data from March 1958 through January 2020, and the model from January 2020 through January of 2050. So, let's head to the future. 4, 3, 2, 1, boom. Well, this is not a very happy plot. It won't affect me. I won't be around then. But I know a couple of kids who will be hitting their early 30s at the top of this curve if something doesn't change. I've always been an optimist, though. I'm hoping that some bright engineer or scientist, maybe one of you watching this video, will figure out a way to get us out of this mess. Gee, optimism or not, this is a pretty depressing way to end this video. So let's don't end this video, at least not yet. Let's look at a few more features of live scripts first, and let's end with the feature that lets us convert a non-live script into a live one. Maybe all these merry little features will help us forget about CO2. In fact, let's just not talk about it, and maybe it'll solve itself. Yeah, that's the ticket. I'm feeling better already. So let's see now. What was the first dandy feature I wanted to show you? Oh yeah, we can add a table of contents. It's so easy. Let's put one up here just after the title. First, let's open up this ribbon and pin it open. There. Now I just put my cursor here, click the table of contents icon up here, and there it is. It shows the heading for each section. And these are live links. If I click on one, no, I don't want to click on that one. Not thinking about that one. Let's click on this one. And it takes me right to the top of the section. And while I'm there, I'm going to show you a feature that's going to knock your socks off and flip your wig. What would you say if I told you that I could add a properly typeset equation for our exponential model right here in this live script? Well, watch this. I click Insert, I click Equation, and this block shows up that says Enter your equation. Well, don't mind if I do. I type CO2 equals A plus B, and then go up here and click the power icon, type E, and click in the box for the exponent and type N, left parentheses, year minus 1958. And the right parenthesis is already here. I want my equation to stand out, so I'm going to highlight the equation by holding down the left mouse button and sweeping over it. Then I'll click this B over here on the left to put it all in a bold font. Now I click outside the equation and the equation editor goes away. And I want my bold equation to be a little bigger. To do that, I go back again to the font size selector and choose, say, heading 3. And what a nice looking equation. But there's something a bit off. It's the CO2. Chemists don't write it like that, and we shouldn't either. I'm going to delete the 2, highlight the CO, click the index icon, and type 2 in the subscript box. Now we've gone from nice looking to beautiful. Feel free to pause me so you can adjust your wig and pull your socks back on. Okay, to see the next superfine feature of LiveScripts, let's click on the tiny down arrow below the Save icon. And would you look at all these save options? And saving into any of these formats uses WYSIWYG. What you see is what you get. So if you run some sections but not others, the document you save to will show only the output that shows up in the LiveScript window. And if you hide the code by clicking the View tab and clicking the Hide Code icon, the code disappears, and no code will show up in the document. If you want output to show from some sections but not all, and yet you need to run the earlier ones to get data for the later ones, just click the Run button to run them all, then scroll down to each section whose output you don't want to show up in the document, click Write and choose Clear Output. So not only does the LiveScript bring your code to life, it gives it a life outside MATLAB via Microsoft Word documents, Adobe PDFs, LaTeX, or HTML. So you can publish your code on paper, electronic documents, or on the internet. And speaking of publishing on the internet, it's finally time to see how to convert a non-live script into a live script. I've got one in a file here in the current folder named theoldway.m. Oh wait, I forgot about the spell. I have to snap my fingers to make it visible. What? Oh, that's right. This one needs a double snap. There. So here it is. And you'll notice that it's divided into sections by means of the double percent signs here and here. And we start with a double percent sign as well. And on that first comment line, I've typed the same title that we used for our live script as the title for this non-live script. Then on the next few lines, I put the text that came after the title. Then I started the second section with another double percent sign and so on. And I've also copied the code from the first 2 sections of the live script into the 2 sections of our non-live script. I've omitted the remaining sections of the live script just to keep it short. Now if I run this thing, a figure pops up with just the second plot. As I explained earlier, what's happened here is that the second plot has replaced the first plot. To keep that from happening, I need to add a figure command before the second plot. So now, if I run it again, 2 figures pop up. And finally, let's click this Publish tab and then click this Publish as HTML icon. The problem with the disappearing plot appears to happen again, but more importantly, a web browser popped up with a nicely formatted version of our non-live script. It's written in HTML, and it has a nice big title, bold headings, and embedded plots. And you get a table of contents with live links automatically. And what about the picture of the CO2 collection station? Well, we can add that by clicking the Image button, and we can add a hyperlink by clicking the Hyperlink button, and an equation by clicking either of these buttons that say LaTeX. Only markup instructions for these objects will show up in the script, but the objects themselves will show up in the published document, either in HTML or PDF, depending on which format we choose. The documents containing the published versions of a non-live script are stored in the folder named Published here inside the MATLAB drive within a folder with the same name as the script. Okay, I promised that I would show you how to convert a non-live script into a live script. Well, it's very simple to do. You just click the tiny down arrow under the Save icon, choose Save As, and when the little Save As pop-up shows up, you just change the extension from M to MLX and hit OK. And that's it. And your non-live script has been promoted to live script. For the installed version of MATLAB, the conversion process is just a tiny bit different. Here we have the same R2019B version of MATLAB, but this one's installed and running on my laptop instead of running up there in the cloud somewhere like MATLAB Online. And I've got the same non-live script loaded in its editor. To convert it, we once again click the down arrow under the Save icon and once again choose Save As. But this time a file browser pops up, and down here where it says Save as Type, we just choose MATLAB Live Code Files with the MLX extension and click Save. And our non-live script has been promoted to live script. And you know what? To show that it's not all about version 2019B, let's go down into my Cellar and pick out another version to sample. I'm afraid I have a strict rule against filming my collection, so I'm going to have to ask the cameraman there to please turn off the camera, would you? Thank you. There's a light switch here somewhere. There. Oh my gosh, would you look at that? 2014B. That was a great vintage. I'll never forget it. And I made some great memories with that one. But live scripts weren't invented until 2016, so that one won't work for us. And neither will this 2015B over here. Although it's a saucy example with hints of blackcurrant and ripe cherries, loamy notes, and a smooth finish. Let's see, what might work here? I've got a 2016B. Here's a 2017B. 2018A. You know what? This 2018B on the top shelf is calling my name. What? Snob me? Doesn't everyone have 7 installed versions of MATLAB on their computers? Really? Well, I like to be prepared for any occasion. And just to show that I'm a fair-minded man, let's run my Mac OS version. Okay, you can turn the camera back on. And here's that same non-live script running on Mac OS. And although it happens to be R2018B, the conversion routine is the same as for R2019B running on Windows. Click the down arrow under the Save icon, choose Save As. A Mac-style file browser pops up, and down here where it says Format, we select the same option, MATLAB Live Code Files with the MLX extension. Click Save, and again, we see that our non-live script has been promoted to a live script. So why do I keep saying promoted to a live script? In other words, what's better about a live script than a published non-live script? Well, the big advantage of a live script is that while you're developing one, you get to see its formatted version changing in real time, which is what puts the live in the name live script. Also, a live script allows you to hide code and/or portions of output, which in some cases might be confusing to the reader. or might even include proprietary code that you don't want to share with the world. And a live script is easier to work with because of the WYSIWYG equation editor and the extra options for layout and type styles. Finally, it allows you to publish in 4 formats instead of only HTML and PDF. Okay, we've seen how to bring MATLAB code to life with live scripts. We've learned how to create them, how to break them into sections, add headings, add a table of contents, and add equations. And we've seen how to publish them as Word documents, PDFs, LaTeX documents, and web pages. And we've even seen how to convert a non-live script to a live script. Along the way, we studied functions for general use that allow us to read Excel workbooks and do data smoothing and curve fitting. And finally, we learned that when global problems are threatening our lives, the best thing to do is not to talk about it, not to think about it, do nothing, and wait for the problem to solve itself. Well, that's a summary of what we've learned in this lecture. There are more features to live scripts, but as we said at the beginning, you can explore the rest on your own after this lecture. Before we leave, though, I'd like to add one more command to our live script, a simple fprintf statement, so you can see what a live script does with printed output. Let's add it as the last command of the last section. And let's run the last section one last time. Well, fprintf must have run, but nothing showed up in the command window. That's because live scripts keep everything inside. Non-live scripts don't. If you run the equivalent non-live script, the printout will show up in the command window, just as it does for a function. But when you publish either type of script, the printout also shows up in the published document. And here it is at the bottom of the script. We can read what fprintf wrote. The predicted CO2 concentration for January 2050 is 510 parts per million. Considering that CO2 concentrations have never once exceeded even 300 parts per million for the previous 800,000 years before 1960, according to Antarctic ice core measurements, there's clearly something going on here. Of course, predictions can only be as good as the input data and the model. Our model is very simplistic. It doesn't consider the actual scientific phenomena. It doesn't include possible positive feedback loops due to surface ice disappearing or the permafrost melting. Nor does it include possible significant emission reductions or the potential impact of future carbon capture technologies. What is clear is that business as usual is taking us down a dangerous path. Hopefully it's not too late to act. Well, that's some pretty heavy stuff. Let's move back to a lighter subject, MATLAB, if I can call that light. As you can see, MATLAB's live scripts make it easy and fun to create highly interactive documents or richly documented programs, depending on the way you look at them. I'm sure you'll find good use for them in your studies or your work.